blocked me on Facebook. And now you're going to die.
Shit!
We'll be discussing password storage. We're going to approach this lesson from the perspective of you creating an application that's going to require users to create a password. Each of these passwords are going to have to be saved somewhere so that later on, when your users log into your application, you can validate that they put in the correct password. You'll be saving these passwords on a disk somewhere, and it's important to save them securely. That's what this lesson is going to be about. There's essentially 4 rules that you have to keep in mind when you're considering secure password storage. So when your users first create the account, they're going to input a password that they want to use. And you're going to store this password somewhere in a file. The idea is when the user logs in later on in the future, you can check the password they put in against the passwords in your file. They'll have a little username and password box, and then whatever they put in here, you can validate against what you have in here. The problem is if your passwords file gets compromised, maybe your hard drive is stolen, maybe someone hacks into your server, or maybe it gets stored somewhere that it shouldn't, or whatever, all of your users' passwords have now are now in the hands of an attacker. The problem with that is often your users are reusing passwords across multiple sites. So Alex might very well be using the password giraffe ! For their email or their banking system, and you don't want a compromise of your system to compromise them thoroughly. Remember, these are your customers you're taking care of here. So the first rule of password storage is you should never store a password directly. You should instead only store a hash of a particular password. So instead of storing giraffe ! What I'll do for Alex is, using a hashing algorithm, only store the resulting digest of Alex's password. You could do this the same for every single one of your users. What this does is that it takes advantage of the fact that a hash is one way. If someone compromises this file, all they're going to have is a digest of the user's password, and it's impossible to take this digest and reverse engineer it back into the original password, the original word. That's one of the tenets of a hashing algorithm. When your users are trying to log into your system, they'll put in a username and then they'll put in a password. And what you can do is hash the password that they put in and see if it matches the digest in your file. If it does, then you know they've put in the proper password. So you can still validate who they are, even though you're not saving their password anymore. In fact, this is why when you lose your password to some online service or whatever, and you go and do a password reset, they can never recover your password. All they can do is reset it, because they don't know your password. They didn't save it, as they shouldn't have. All they know is a hash of your password, and even they can't reverse engineer your password hash back into the original password. That is why when you lose a password to your email account or your banking system or whatever, all they can do is reset it to something new once they've validated it that you are who you say you are. So the first rule of password storage is never store a password directly, only store the digest of your user's password. We have 3 more rules to go, so let's keep going. The problem with only storing the password hash is there's a thing that exists known as a lookup table. It's impossible to reverse engineer a particular digest into its original word. But if someone takes the time to calculate every MD5 hash of 1-letter characters, and then every MD5 hash of 2-letter characters, and then every MD5 hash of 3-letter characters, and then 4-letter characters, sooner or later, they're going to know what every single word, they're going to know the digest for every single word in the English dictionary. Or more, if they do a complete brute force lookup table. Which means at some point in time, if an attacker started creating this lookup table, they're going to have a list of every single digest for all character passwords and the original word that created that password. Then, if your password hash file gets compromised, all the attacker has to do is look up a digest in their table to find the original word that created that digest. So simply storing the MD5 hash, or simply storing the digest of a particular password, isn't enough for full password storage because of these things known as lookup tables. These days, you should assume that any password that is 1 to 10 digits of any complexity, meaning uppercase letters, lowercase letters, etc., has their digest that exists somewhere in the lookup table. To give you an example of a lookup table, there are some we can look at that are online. One of them is available at crackstation.net. You'll notice the crackstation.net lookup table is a pre-computed lookup table of a bunch of password hashes. What this allows you to do is put in a list of hashes. These are the exact same hashes that we have here in our example. Complete the reCAPTCHA. Hit the crack hashes button, and if we wait a couple seconds, you'll notice they are able to find an exact match for every single one of the passwords in our example. So again, they didn't reverse engineer the digest into the password. They simply had already calculated every possible word and the resulting MD5 digest and simply looked it up into their particular table to find that this particular digest mapped to this particular word. So because of lookup tables, simply storing the hash of a password isn't enough, and we have to go a step further. That step further is combine the password with what is known as pepper before creating your hash. Pepper is simply a unique string for every single password database or application. So the application you create is going to have a different pepper than the banking system or their email system or their social media profiles or whatever. Every different system will have a unique pepper. For the case of our example, we're going to go ahead and use the pepper of INE's number 1. So the way it works is instead of simply hashing the password directly, I'm going to combine the password with a pepper and then run it through a hashing algorithm, and that's going to give me the more secure digest that I can save in my password file. Notice only this part is saved in the password file. The password is not saved, nor is the pepper saved. Using a pepper does a few things. One of those things is that it guarantees a minimum length and complexity of what is hashed. Earlier we told you every combination of password that is 1 to 10 characters is essentially exists in a lookup table somewhere. But what this does is it guarantees that no matter how small or large a user uses for a password, you're always combining it with a certain amount of letters. Moreover, you're combining it with some capital letters, some special characters, some numbers, some lowercase characters, so you're guaranteeing a certain complexity and certain length of everything that is being hashed. What this is going to do is force lookup tables to be unrealistically large, or force the creation of lookup tables to take an unrealistically long time. It might take thousands and thousands of years to put together a lookup table of every single of the result of the MD5 hashing algorithm for every word that is 14 characters long, which would be required to crack Jordan's password over here. So this protects your users from having their hashes looked up in a lookup table. So the second rule to proper password storage is to combine the password with a pepper before calculating the hash. But again, that isn't the entire story. Notice our users Kelsey and Dylan use the same password. Well, if the same password was combined with the same pepper, then the same digest is going to result in the passwords file. There are stories of hackers creating thousands and thousands of accounts using, say, the top 10,000 passwords list, and then compromising the passwords file. Then all they have to do is find which of the digests of their fake accounts match which of the digests your users use. They're not going to be able to compromise the passwords for every single one of your users, but there's a good chance that they'll find a lot of similar digests for some of your users that happen to be using a password in the top 10,000 passwords list. Moreover, pre-computation is still to some degree possible. The pepper is not going to be saved in your passwords file, but it is going to exist in your application code somewhere. So it's possible for a motivated enough attacker to acquire your pepper, and then they can create their own lookup table combining the pepper with every 1 character password, and then the pepper with every 2 character passwords, and the pepper with every 3 character passwords. They just need to run through every iteration, and sooner or later they'll have a unique lookup table specifically for your application. So some manner of pre-computation is still possible if all you use is pepper. Which brings us to the third rule of proper password storage. The third rule of proper password storage is that passwords should be combined with what is known as a salt before creating your hash. A salt is a random string generated for each user. So when Alex creates an account, I'm going to randomly generate a particular salt. I'm going to combine that with the password they provide, and I'm going to combine that with the pepper from my application, and all three of these will be hashed together to create the digest list. To show you an example of that, the new digest is now a combination of the user's password, the pepper, and the salt. The salt should be generated randomly for every single user, but it should also be re-randomly generated every time the user changes a password. The idea is no password instance should ever share the same salt. Moreover, salt should be of a certain length. We simply use a 12-character salt for the simplicities, but ideally the salt should be the same length as the actual message digest. If you're using MD5 as your hashing algorithm, which produces a 128-bit digest, you should have a 128-bit salt. What this does is it defeats every possible pre-computation lookup table. If an attacker wants to crack Casey's password, the attacker would have to find Casey's salt in the passwords file, discover the pepper in your application code somewhere, and then combine the pepper with the salt with every 1-character password, and then every 2-character password, and every 3-character passwords, and every 4-character passwords, and so on and so forth. This would force the attacker to brute force every single password every single time from zero. Nothing that has been pre-computated in the past will be able to be used by the attacker to hack one of the user's passwords. The salt is going to have to exist in your passwords file, because when your user logs into your application, they're going to put in their username, and then they're going to put in their password, and you'll take the password they put in, look up the salt for that particular user, combine it with the pepper, combine it with their password, and then see if the resulting digest matches what you have on file. So even with the salt, you can still validate that the user put in the right password. So the third rule to proper password storage is that passwords should be combined with the salt before calculating the hash. Now there is some debate about if you use salt properly, do you actually need a pepper? That is still heavily debated in the crypto community. One thing is known for sure though, is the pepper definitely doesn't weaken anything. So it might strengthen the password storage, and it definitely doesn't weaken the storage, and it's rather cheap to implement. So it's a good idea to do so. So the first rule of password storage is always only store a digest of the password. The second rule was combine it with the pepper. The third rule was use the salt, which finally brings us to the fourth rule of password storage, which has to do with which hashing algorithm you choose to use. And we've been using, as an example, the hashing algorithm of MD5. MD5 and SHA or SHA-2 or even the SHA-3 family are built for speed, which makes them really good for validating integrity on bulk data transfers, but not so good for password storage, because since they are so fast, it allows hackers to create lookup tables at a very high rate, because they can run billions and billions of these algorithms per second. An ideal hashing algorithm for password storage would be one of these. These work the exact same way as a hashing algorithm, which is to say they produced a fixed length fingerprint of the original content that you hashed, except these four include an internal delay or an internal slowdown function, which means you can tune these to take up to a second for every single calculation. Now when a user is logging on, that 1 second it takes to validate that they have the right password, that's not a big deal. But if an attacker is trying to create a lookup table and they need to run 1 trillion iterations of the hashing algorithm, that's going to take 1 trillion seconds, which is something in the vicinity of 1,000+ years. So using these slower hashing algorithms makes creating a lookup table unreasonable. On this list, Argon 2 is your most secure by current standards, followed by Bcrypt and Scrypt, and then if either of these three are not available, PBKDF2 is an option. So in total, we talked about 4 different rules for password storage. The first rule was never store the password in clear text. You should only store a digest of the resulting password. The second rule was to use a pepper, the pepper again, which is a unique string for every single system or application. The third rule was to use a salt. The salt again is a unique string for every single user and every single user's password. And finally, use a hashing algorithm with a built-in slowdown function to prevent attacker from being able to create a lookup table using the digest in your passwords file. In this lesson, we learned that passwords should be stored safely by combining them with salt and pepper within a hashing algorithm built specifically for password storage. I hope you enjoyed this lesson. I want to thank you for viewing, and I'll see you in the next one.
You blocked me on Facebook, and now you're going to die.
Shit!